Welcome. You're going to look at exponential models. Many of you would have done this in high school algebra or pre-calculus classes 1140 and 1130. We will do an example refreshing your memory about those things, but we can use differential equations to explain why we use exponential models in the situation we do. We'll start by solving a simple differential equation, dn over dt equals k times n, where we assume we have an initial value given by n equals a positive number when t is 0. The given equation is a separable equation because I can cross multiply and then divide both sides by n. It gives me dn over n equals k dt. Since k is a constant, all the n's are on the left, dt is on the right. It's a very simple integration because on the left I have dn over n. Let's for the moment assume that n is positive. I'll explain later why it has to be positive in general. So on the left, an antiderivative is just ln of n. On the right, it's kt plus c with the constant just on one side, and as usual I put it on the right. Now I'm going to find c by plugging in the initial value, 0 for t, n naught for n. So I get ln of n naught equals k times 0 plus c, so c is ln of n naught. Plug this back in our general solution and then solve for capital N. So I need to get rid of ln. I need to take exponentials of both sides to do that. So n equals e to the power kt plus ln of n naught. If I have a sum in the exponent, I can write it as a product. So I get e to the kt times e to the power ln of n naught. E and ln are inverse functions, so e to the power ln of n naught is just n naught. And we customarily put it in the front. So we get the solution n equals n naught e to the kt. So now why didn't I need to worry about the absolute value here? Strictly speaking, at this point, all I can say is that absolute value of n is this quantity. Since n must be a continuous function because it's differentiable, the exponential must always be positive. If n naught is positive, then this is always positive. And since n cannot change sign and it starts at a positive number, must always be positive. So they should be equal. Of course, if n naught is negative, then product will be negative, and n has to be negative always because it starts out being negative. So I don't need the absolute value. So let's look at what this says. This equation says if you have a function with constant relative rate of change, the rate of change is proportional to the function, then only solutions are exponential models, a constant times e to the power constant times time. So in situations where we expect to have a constant relative rate of change, we can use exponential models. And the standard examples are situations where this makes sense. If you take population growth, all other things being equal, a population which is twice as big should be expected to have twice as many births and twice as many deaths. Net rate of change, birth rate minus the death rate, should be proportional to the population. If the population is twice as big, the net rate will be twice as big, so on. Another example is radioactive decay, where quantum mechanics tells us that if you have twice as much radioactive material, you get twice as much radioactivity, so twice as many atoms of the radioactive material change in a given period of time. So again, the same thing. Now, there is one important point which often is not mentioned in pre-calculus courses. Exponential models can be written in the exponential form or the logarithmic form. Sometimes it's more convenient to use the logarithmic form. I will illustrate that in an example in the next session.